Hello and welcome to another lecture on linear programming problems. Today we shall be discussing about optimal feasible solution for a given linear programming problem, and later we are going to deal up with some numerical problems that would be based on finding the optimal feasible solution for the given linear programming problem. So starting with optimal feasible solution, as we have discussed earlier also, that optimal solution is a feasible solution which maximizes or minimizes the objective function, and an LPP may have 0, 1 or more than one optimal solution. Now, as discussed earlier, feasible solution represent the common region determined by all the constants of an LPP, and every point in this region is called the feasible solution to the given linear programming problem. Now, the feasible region is always a convex region, meaning that if any two points in this set are joined by a straight line segment, all the points on this segment will lie in this set. Next, we are going to discuss a numerical problem that is based on finding the optimal feasible solution for the given linear programming problem. Now, according to this problem, a company has two factories located at P and Q locations and has three depots situated at A, B, and C. The weekly requirement of the depots at A, B, and C is respectively 5, 5, and 4 units, while the production capacity of the factories at P and Q are respectively 8 and 6 units. The cost of transportation per unit is given in the table, and we have to find out the units that must be transported from each factory to each depot in order that the transportation cost is minimum. Now here we have to find the units that must be transported from each factory, that is P and Q, to each depot, that is A, B, and C, in order that the transportation cost is minimum. Now we take a look at the table given. Now here we have the cost of transportation from factories P and Q to depots A, B, and C. Now we have from P to A, the cost of transportation is 160. The transportation cost from P to B is 100, and transportation cost from P to C is 150. The cost of transportation from factory Q to depot A is 100. From Q to depot B is 120, and from Q to depot C is 100. And it is given in the question that the weekly requirement of the depots A, B, and C is 5, 5, and 4 units, while the production capacity of P and Q are 8 and 6 units. Now, as given in the question, we note that the total production of P and Q is equal to 8 plus 6, that is equal to 14 units, and the total weekly requirements at depots A, B, and C is equal to 5 plus 5 plus 4 as is specified, and thus we have the value of total weekly requirement of depots A, B, and C equal to 14. This shows that there is no mismatch between the supply and demand. Now let's suppose factory P supplies X units per week to depot A and Y units per week to depot B, so that it supplies 8 minus X minus Y units to depot C, since the total production capacity of P is 8. Now obviously X is greater than equal to 0 and less than equal to 5. Similarly, Y is less than equal to 5 and greater than equal to 0, and the amount supplied to depot C by factory P lies between 0 and 4. Now the given data can be represented diagrammatically as shown. Now here we have factory P, which produces a total of 8 units and a factory Q which produces a total of 6 units. Now as depot A's requirement is 5 units and it receives X units from factory P, that means it's receiving 5 minus X units from factory P. Similarly, depot B requires 5 units and it's receiving Y units from factory P, that implies factory Q is providing 5 minus Y units to depot B. And similarly, since the capacity of depot C is 4 units and it is receiving 8 minus X minus Y units from factory B, this implies that factory Q is providing depot C with 4 minus 8 minus X minus Y units, which is equal to X plus Y minus 4. Just as a cross check, we are going to check the quantity supplied from factory Q to depots A, B and C, which is sum of 5 minus X, 5 minus Y and X plus Y minus 4, which is equal to 6 units and is equal to the amount that is produced by factory Q. And thus the total transportation cost in rupees is equal to 160 into X plus 100 into Y plus 150 into 8 minus X minus Y plus 100 into 5 minus X plus 120 into 5 minus Y plus 100 into X plus Y minus 4, which on simplification gives us a value of 10 into X minus 7Y plus 190. Hence the given problem can be formulated as an linear programming problem as find X and Y which minimize Z, that is the objective function, which is equal to 10 into X minus 7Y plus 190 and is subjected the constants X plus Y is greater than equal to 4, X plus Y is less than equal to 8, X is greater than equal to 0, X is less than equal to 5, Y is greater than equal to 0 and Y is less than equal to 5. The feasible region corresponding to these inequations is shown in the figure. It is bounded region A, B, C, D, E, F. We can calculate the values of Z, that is objective function, at these 6 corner points as shown in this table. Now corner point A with coordinates 4 and 0 has the value of the objective function equal to 1940. Point B with coordinates 5 and 0 has the value of Z equal to 1950. Point C has the coordinates 5 and 3 and thus the value of objective function is equal to 1740. Point D has coordinates 3 and 5 and corresponding value of Z equal to 1580. Point E has the coordinates as 0 and 5 and Z is equal to 1550. Similarly for F, whose coordinates are 0 and 4, the value of objective function is equal to 1620. Thus we see that the objective function is minimum at 1550 at point E, whose coordinates are 0 and 5. Hence X equal to 0 and Y equal to 5. Thus for minimum transportation cost, factory P should supply 0, 5, 3 units to depots A, B and C respectively, and factory Q should supply 5, 0, 1 units respectively to depots A, B and C. Thus we have found the optimal feasible solution to this given linear programming problem. With this we conclude this lecture on linear programming problems that was based on finding the optimal feasible solution for a given linear programming problem.